All right, so this video is on the volume of a parallelepiped. So at this point, we've already learned that the area of a parallelogram, we actually learned a couple different formulas for it, but the one that I want to use, so area of a parallelogram determined by U and V. So U and V are down here, they're in the same plane, essentially. Well, they define a plane and a parallelogram. And so the area was the magnitude of U cross V. And so the volume of this slanted box, essentially, would be the area of the base, which is this guy down here, the shaded part, times whatever the pure height of the box is. Not this slanted height that's defined by W, but the height that would be if you kind of looked at just how tall W was. So this component of the W. So I'll kind of do this here. So if you just sort of looked at how tall W was, I'll call this H for height, right there. If we multiply that by the area of the parallelogram, then we get the volume of that parallelepiped defined by U, V, and W. Okay? So the idea of this axis sticking straight up perpendicular to the plane of U and V, well, that we can find a vector that's normal to the plane defined by U and V, and we know that U cross V is orthogonal to both U and V. So this normal vector we could think of as U cross V right here, okay, or perpendicular vector if you want to think of it that way. And I don't know if you can see it down here, but that U cross V vector is, it's noted that it's perpendicular to U and it's perpendicular to V. So it's got to be orthogonal to both. And we learned that this dot U or this dot V is 0. So they are orthogonal. And as long as they're all non-zero, then they're perpendicular too. Okay, so the volume of the parallelepiped will be the area of the parallelogram times H. Right? Okay, so that's the magnitude of U cross V times H. All right. Now H is really the projection of W onto U cross V, right? So this is really U cross V, whoops, times the projection, it's the length of the projection. So the projection would actually be this vector right here. What I want is the length of the vector. So times the length of the projection of W onto U cross V. So there's the notation for it. Let me move that over. U cross V would be the subscript there. Okay. So we learned earlier about projections. H, then, I'll rewrite this, length of projection of U cross V, of W onto U cross V. That's the way to read that. Well, that's really the scalar component, right? It's the component of U cross V, or sorry, of W onto U cross V. And the component might be positive or negative. In this case, we want to treat it as, since it's a length that we're looking at, we want to treat it as a positive, right? If it's negative, it's really just pointing downwards instead. And so then you could say, well, okay, so this whole parallelepiped is upside down, but the volume doesn't actually change, so you want to ignore the sign. And we learned the scalar component was equal to, and in this case, it's going to be the main vector W, and then dot, and then it's this vector over its magnitude. It's the normalized version of U cross V. So it's U cross V here over magnitude u cross v. Okay. So this is just what the h is, which is this part right here. Okay. So I'm going to rewrite this now. V equals the magnitude of u cross v, and then times, and then this absolute value thing right here, w dot u cross v over magnitude of u cross v. And then we can do a little bit of manipulation with this thing. So the magnitude of u cross v, the magnitude of any vector, so u and v are non-zero here, so this magnitude is also non-zero. The magnitude of u cross v is going to be positive, right? So I can take it out of the absolute values and just keep it in the denominator. So let me rewrite it this way. So now it's u cross v, that first u cross v, times, and then the absolute value of w dot u cross v in parentheses here, all over magnitude of u cross v. So I'm just pulling out a positive term from that absolute values. And we know that I'm multiplying and dividing by the magnitude of u cross v, so these guys will cancel, and I'm left with absolute value of w dot u cross v, just like that. Okay, so that's the volume. That's actually not that bad a looking formula right there. Okay, now in a homework assignment at some point, you learned that w dot u cross v, since these are going to be 3D vectors, you can calculate that by using determinant u1, u2, u3, v1, v2, v3. And that thing's called the triple scalar product. And you might remember that if you interchange two rows, that would be like interchanging two of these guys, and all it does is it flips the sign, right? So if I switch w and u, I would get the same determinant, the same scalar out of this thing, except that the sign would be the opposite of whatever I got for this particular one that's showing right now. Well, so it doesn't really matter when you're finding the volume of this thing, which one you call w, u, and v of those three vectors, because they're in absolute values anyway. So either you're going to get a positive or a negative inside. Doesn't matter what order, the actual number value will always be the same. And then when you take the absolute values, the sign goes away anyway. So there's the volume formula right there. Okay, I hope that helps a little bit. And I think that covers it. All right, I'll see you guys soon.